Welcome everybody to this week's Happy Maths Hour, and we are investigating circles. So if you want to join in, I've got a compass, but we're going to show you how to make a compass with a paperclip, and I've got circles everywhere and a ruler and lots of nice, lovely ways of learning about circles. Toni.
Well, yes, and we're going to do some paper folding. We're going to use cardboard and pins, and I'll also show you a gearboard that I've made, and you might like to make one of those. So it's all about circles. And of course, circles occur everywhere, don't they? I mean, you see circles around us occurring naturally, and here they are, ripples in some water, probably raindrops. That's very attractive. And here are some more circles. Lots of designs with circles. And you see there are three wheels, three pictures with wheels in them, which show how important for vehicles. And these are two bicycles and a Ferris wheel, but of course, all sorts of vehicles have to have wheels to run along, to roll along. Do you like the Russian dolls?
I love the Russian dolls. I was wondering where the third wheel was, the third picture with wheels. And I'm like, oh, I hadn't thought of the Ferris wheel. I really love the Russian dolls. I mean, they've been put into the shape of a spiral, which is increasing the size in that spiral. But each face is kind of surrounded by a circular shape. Right in the center of the spiral, where the little dolls start, there are circles in the center. They're concentric circles, and I think there's a circle behind on the wall as well.
It's the biggest set of Russian dolls I've ever seen. Most sets have got 6 or 8 in them, but
and the smallest one as well. I don't think I've ever seen anything quite that small. Beautiful.
Yes. And here are some stone circles, which are usually associated with some sort of rites of to do with the solstices and observations of the sun setting and rising. And here is Stonehenge, a familiar stone circle in the UK. But they do occur all over the world, as many around the Mediterranean countries.
I had no idea there was a stone circle in Somalia. I didn't know there was one in Portugal. In fact, I knew of some around the world, I think in South America, I'm not sure. But this is fascinating.
Yes.
Finding that people independently all around the world are creating stone circles. I mean, there's no way that people from Stonehenge had any idea of what was happening in Israel or Somalia or even Portugal at that point.
And they were built many thousands of years ago. I mean, some more recently than 7,000 years ago, but it is something about the circle which has fascinated people, and maybe it's because they observe the sun and the moon as spheres, as circles, and they are forming these stones. And as you see with the picture of Stonehenge, it's often observations of the sun and moon that they make. The stones are just placed so that the sunset or sunrise can be seen between two big stones. So here are some more pictures of stones. There's another stone circle there, but I love the pile of oranges. I mean, I often see piles like that sometimes of tins in a supermarket, and very often piles of fruit on a fruit stall. But I haven't ever seen one as big as that pile of oranges.
Yeah, I feel sorry for some of the oranges at the bottom there. They have got to be being squished. But it's beautiful. And they must have chosen oranges that were very similar in size. I thought they were Ferrero Rochers. I thought they were little spherical chocolates, because that is incredible. If that's all oranges, that you could estimate how high that is just by knowing the size of a normal orange, an average size orange.
Of course, you've got the square-based pyramid there, like the pyramids of Giza. And then you see the eggs are round, but the bees' eggs are round, but they fit into the hemispherical packing, which is the typical honeycomb. And what you see on the right, that huge stone, then the two on rollers, not wheels, but rollers.
They're like logs.
Yes.
And they probably are logs, actually. They probably are trunks of trees.
And then as you roll it forward, a log rolls out the back and you run round with the log and put it under the front before you continue to pull this heavy load along. And of course, that was me and
my brothers when we were little. My dad got this little, very heavy sailing boat, very, very quite primitive one, but it was very solid wood. And we could only get it onto the beach a little bit. We had to push it onto the beach. And then we got these rollers. And my job was to catch them at the back, two of us, and run round to the front and put them down in front of the boat again so that we could get the boat up the beach safely out of the waves.
Gosh. Well, there you are, you see. That was a very ancient way of moving heavy objects, and a very efficient way, really. But very absolutely necessary, because these stone circles were often built very far from where the stones were originally formed and found, and then formed into the right shape and brought to the site of the stone circle.
Yeah.
Now here, let's get down to some paper folding ideas. And here on my slide, you see a piece of paper, and I just drew around a dinner plate to cut that out. And Caroline has made one as well. And I marked a diameter, and it's easy to find a diameter. You simply, Caroline will do it. You fold the circle in half.
I'm going to make my image bigger. So what you do is you fold the circle in half. I'm going to demonstrate it. So there you go. I folded it along one of the diameters in half. So that's to find the diameter. So as long as it's going through the center. So anyway, I folded it in half. It's exactly in half. Now what do I do?
I should unfold it and make another fold along where it says radius. Fold it along there.
Right. Fold it along there again in half.
Yes.
Okay. So we know,
You've got two of the diameters will intersect at the center. So you now found the center.
Okay, we found the center.
And also, you can measure the length of the diameter, and if you like, you can just by bringing the two along that where it says radius, bringing those two pieces of circle together, you can see that the two radii, that the diameter is equal to 2 radii.
Right.
Match radius to the diameter, so you can see it's half the diameter.
So put the radius literally, align the radius right on the diameter.
Caroline, you can do it various ways. I think anybody, yes, you can see by just folding the radius in half. You can see that throwing the diameter in half. You can see the radius. 2 radius lengths make a diameter length.
Well, that's nice. That one right there, what you just said. I folded it in half, and so that length is the radius, and that length is the radius. So 2 radii make 1 diameter.
Yes, and you can do that. You can show that many different ways.
Yeah.
And you can see that Caroline's written down part way around is called an arc. And if you go all the way around the outside of the circle, that's called the circumference.
So that's the arc. And all the way around, the complete circle is the circumference. Obviously, start and finish in the same place. So starting there, all the way around, back to there again, all the way 360 degrees. That is the circumference.
Now, what it said on the, you haven't got B marked, Caroline, or D. On the screen, you see.
Oh, yes. I've got D marked. I forgot to mark
and
B.
B is, the line AB is the one that goes through the radius. And and what it says here is fold A to B and then C to D. And what do you notice? What do you notice if you
Okay,
fold A
okay,
to
hold
B?
on. A to B. So I haven't done this. I didn't see that bit.
A to B.
I just got the props ready. I've got A
and
to
they're
B.
the same. And then that you see that what you saw before, that
I've
the
got a semicircle.
radius is half the diameter.
Right? And oh, C to D was what we did. Yeah, we already did C to D, and it's exactly the same thing. A to B and C to D, you get the same effect.
Yeah, exactly.
Okay.
Exactly.
Okay.
Exactly. So we're just exploring where is the center and learning some words. Now, here's a little picture of the paperclip compass. Have you got a paperclip compass?
I do. I have a paperclip compass right here. I've got this. Move this bit of cardboard away. We're going to need the cardboard in a second. But for the
compass is such a neat way of drawing a circle.
So what I've got is one pencil. I'm going to take this other pencil. I'm holding this one tight. The one that's on there. I'm holding it tight. And now I'm going to fully extend the other one. Go all the way around. I hope it stays within the view. I'm going to bring it round this way. And hey presto, we have a perfect circle.
And of course, if you have several paper clips of different sizes, you can draw circles of different sizes.
Yep, I've got now that you remind me. No, I haven't got. I did. I saw it last night, and I forgot where it was. I've got a giant, giganormous one. Rightio, let's move on.
Let's move on. So, how about having a look at the next? Can you see the slide on the screen? Yes, I think
I'm going to. I can. I've got my.
And Caroline has got her cardboard circle, and she is going to put in a pin at the center.
Just a bit of extra thickness here. There we go. Right, pin at the center. Plonkety plonk, got the pin.
And like the picture on the screen, she's going to put 2 pins below the center.
Just anywhere, yeah?
Yes.
Okay.
And she's going to put a rubber band, as you see on the slide, that goes around those 3 pins.
Right. Rubber band, rubber band, rubber band. Whoopsie. Rubber band's too short. Okay.
No, stretch it. Stretch it.
Yeah,
it can't be
yes, I know,
short.
but it's pulling the pins out, Tony.
Oh, well, you have to push the pin in hard.
I need some more thickness of cardboard. 1 second.
Well, if you can't do it, Caroline.
I can. Where there's a will, there's a way.
Well, while you're doing that, I'm going to show you my. There we go. Can you see my gearboard? Now this is made. Caroline's.
No.
Caroline
hold on.
is.
Tony.
Well,
Tony.
we're just showing the gearboard.
Yes, but
Caroline.
they can't see it.
They can see me, and it's in front of my face.
Tony, they can't. Trust me. Right, show the gearboard. Right, they can see you now.
Okay, here's the gearboard, right, in front of my face. And what you can see is what Caroline is trying to do with her cardboard circle and pins. Here it is on the gearboard. Now, the gearboard is made with a piece of wood and pins knocked in around the circle and one in the center. And what you can see here, as you see on the slide, is that this band, which goes around from the 2 lower pins up to the center, makes an angle. And then I have got another pin at the top here, and the same rubber band is stretched over that. Now, with a piece of paper, you can make the angle, and what you can show is that the angle
Right, I've got that, Toni. I've got that set up.
Okay, well, Caroline is going to show you that in a minute. I'm just going to show it you with the piece of paper here. It's not so good as showing it with a small screen.
We're over
I'm
here,
going to let
Toni.
Caroline do
We're
this
over here.
now.
You
Yes.
weren't on a small screen, but you were pointing it. I don't know where you were pointing it.
Okay,
Where
Caroline.
you're looking is not where the camera is.
Okay, Caroline.
Okay, right. So I've got it set up. So we've got the arrow shape.
Now, Caroline, with your piece of paper, I think you can show something about the angle at the center there.
Now let me just move that so that it matches my piece of paper. So there. So right. So we've got this piece of paper is the same the same size as the same angle as
you need a much thinner rubber band, Caroline. That's the lesson. A very thin rubber band won't be a strong elastic, and therefore it won't pull the pin out.
Right, and I've also got I did actually pick up some longer ones, but they're not. But anyway, never mind. So there we go. We've got an angle that matches the angle that the elastic band makes here. But now watch this. That is the angle. If I fold it in half, exactly in half, and I place it at the top angle, it basically demonstrates that the angle to the center between the two
subtended by the same arc.
Subtended by the same arc
is twice the angle at the circumference.
Twice the angle at the circumference. So the angle to the origin, to the center, is twice the angle at the circumference. Hey, presto, who knew?
Okay, well, there it is. We're just done with paper. You can do it equally well with paper and the lines drawn on the paper. But we thought Caroline would have fun with her cardboard there.
Yeah, I'm learning things about that. Yeah, use different.
Actually, what Caroline is demonstrating is that you do need to, if you're going to do a demonstration in class, you really need to have practiced it a little bit beforehand. So,
and you definitely don't want to have pins flying around in class. Like I just had a pin flying across the room.
No, you're safer with a Gearboard, actually.
Yes, well, yeah, that's a much better plan.
Yeah. Okay, so let's move on a bit and let's look at the slide now. Focus on the slide. We don't need to see Caroline's demonstration, actually, but if Caroline wants to follow this with a demonstration, that's fine. What she's showing us at the moment is shown in the middle picture at the top there, that the angle AOB is twice APB. Okay. Now then, let's look at this one.
I've got that one here as well.
And let's look at this one. Now, of course, P can be anywhere around the upper part of the circumference to correspond with what we see in the first picture. But P can actually be anywhere on the circumference.
So it could have been here, anywhere around there, around the top part. And I was puzzled about that. So where would it go? And what it does is it goes below the origin.
Well, just put it in like the diagram that you see on the screen.
There it is. Got it.
So that PO and that line from P through O, you see there, it's all in a line. And then P is still half the angle. Angle APB is still half the angle AOB.
So that angle there is still half. So this angle hasn't changed, and that's the critical part. The angle that
AOB hasn't changed.
AOB hasn't changed, and so the other one APB hasn't changed. As you move it round, it's still half.
As you move it round, that angle APB is always the same. Isn't that nice? Now then, we're going to move it right round. So now it's below the two pins A and B.
Right. So we're going to have a rectangle.
No, we're not. We're having a quadrilateral.
I mean a quadrilateral. I did mean a quadrilateral. I said it wrong, didn't I? I really, really said it wrong. There we go. Now oh, that's much easier. I can let it go now.
Okay.
So now what? So this angle AOB hasn't changed. So,
yes, but we're not looking at the interior angle at AOB now. We're looking at the obtuse angle AOB above where Q is.
This one, where Q is.
On
so for this one, we're looking at this angle here.
That angle is twice the angle between at the bottom, APB. P is your yellow. Is it a yellow pin, Caroline?
This P is yellow, yeah.
Okay. And so it's still the angle. These angles are subtended on the same arc, and the obtuse angle AOB is twice the angle APB, where P is below.
So let me just, I'm actually going to draw that. So this angle here is twice this angle here.
Yes, yes.
Wow, okay.
And it's easy enough to prove, but we're not going into formal proofs today. But you can demonstrate it with paper, folding the paper and just cutting out the angles and folding it in half like Caroline did, with P anywhere on the circumference.
It certainly makes it easier to learn and understand these, rather than it just being words, because
yes.
I have to say that the description is, what was it? Subtended on the same arc. The angle at the circumference subtended on the same arc is quite a...
Well, you can say sitting on the same arc if you like, but the proper mathematical term is subtended. If you call it sitting on the same arc, that's what it means.
Right. Well, that's helpful.
Now here, it's the same idea, but here A and B AB is a diameter. And what do you notice about that?
Okay, let's have a go. Whoa. Make sure we've got a straight line there. So make sure it is the diameter. So we've got A, B, and now I'm going to make a triangle. Let's see. There's that triangle. Okay.
What she's doing is having an angle subtended by a diameter, sitting on a diameter.
Sitting on a diameter. Let me just get the light over here. And because I'm noticing something very nice about it, no matter where I put it, the angle's the same.
But what is it, Caroline? What angle is it?
I do believe it's 90 degrees. I believe it's a right angle.
So perhaps you could get the corner of a piece of paper and check that.
I certainly can. Let's have a look. It's what corners of pieces of paper are for, isn't it? Let's have a go. Just a normal piece of paper. Let's see if I take... No, I can't take that one out.
What are you doing, Caroline? Where's the diameter, Caroline?
I'm going to place the diameters.
Okay, so that's right. So
there we go. I found a way. There we go.
That's great. That's great. So you can see that is a right angle. And if Caroline puts that yellow pin somewhere else, the point P, as we've called it, she'll be able to show that the angle is still
90 degrees.
Okay.
And I'm intrigued. Let's bring it all the way around here. All the way around. I suppose it's... Whoopsie. Yeah, there goes another pin. There. And hey presto, that is also 90 degrees. That's beautiful.
You can also demonstrate this with string and if you haven't got rubber bands. So it's another thing, another possibility. And you can do it with paper as well. So now we'll move on. So we'll look at the next slide. And so we've got a chord here. Caroline, can you mimic this with your cardboard?
Yes, no, I've got, yes. That one wasn't so maybe, you know what I can do? I can just cut. Oh no, I can just use, I know what I can do. I can just use the one elastic band one way and one elastic band the other. There you go. That's it. There you go. There's one elastic band. And now if I attach another elastic band over here and pull it across, and I can literally just, now the important thing here is what I've got, that has to be perpendicular.
Well, now move the yellow one, Caroline.
Yeah.
So now what you've got is a chord. The red elastic band is a chord. And if Caroline moves the yellow one so that the two elastic bands are at right angles, what you can see is that this radius that she's holding, the yellow elastic band forms a radius, and that halves that chord. So you can do it with paper probably more convincingly. Okay,
hold on.
I think it's a better demonstration with paper.
It halves the chord.
Yes.
Oh, right. It bisects the chord.
Bisects the chord.
Yeah.
Okay, now you've chosen the harder word, Caroline.
Yeah, because
I think this is a better demonstration with paper, actually, Caroline. So why don't you do it with paper?
Right. Let's have a go.
Paper circle.
Paper circle. Got a paper circle. I've got a plain one. Here's a blank paper circle. Right.
Right. So you don't want your pins and your cardboard now. You just want the circle.
I've got my circle.
Fold a segment to make chord AB. As in the picture on the screen. Right. So you can mark A and B, the ends of that chord. Unfold it and mark A and B.
Right.
Now, fold it so that A and B coincide.
Okay.
Now, if you unfold it, you should see that fold goes through the center, and you should be able to mark that diameter as CD, and P as the point where the diameter, the fold line that you've just made, where the diameter cuts the chord AB. Now, because you made the points A and B at the end of that chord actually coincide, kiss each other, come together, what you've done by construction is you've made AP and PB equal.
So I was the line I created, the diameter I created, is bisecting AB literally by the way I made it.
Yes. Now look at AC. Look at
where's
draw
AC?
CB. Draw
second. I've got AC. C's here.
Now draw AC.
Draw AC. So that's going to be I'm going to make a triangle now.
Just keep following the instructions.
I'm just following the instructions. Join AC. Yep. AC and CB.
And join CB. And BD.
And BD. D is this one up here, I presume.
And DA.
I'm going to go fly a kite any minute now.
Yes, it's a kite, isn't it? It's actually a cyclic quadrilateral because the four vertices are on the circle, but it's actually... Why did you say it was a kite, Caroline? Tell us about kites.
Well, kites have symmetry, and you've always got the two adjacent edges are the same. So you've basically made up of two isosceles triangles to make a quadrilateral.
So the two isosceles
triangles,
got a line
you've got your line of symmetry along the that join the opposite ends that are not symmetrical.
So the isosceles triangles Caroline's talking about are ACB and ADB, and the two big triangles ADC and BDC.
Those are there, but they're going to be right angle triangles.
And they're the same, aren't they?
They're the same. Yes, that one is the same as that one, but they're both right angle triangles.
Yes, so those two angles are right angles, and the instructions here say measure, and you don't need to do it now, Caroline, but I think we'll just talk about it. You can get, if you're working with children, if you're teaching, you can get them to measure the angles and lengths of the edges of that quadrilateral, and to talk about what they notice about the angles. And Caroline's already said that the angle DAC and DBC are right angles. And they might notice that CD is at right angles or perpendicular to AB.
There's something else, though, and that is that is ADB half of ACB? Have we got that?
Is
this angle half of this angle?
Why should it be, Caroline?
I don't know, because we had it before.
If you think it might be, then you could do some measuring to find out. It's not the same as we had before, with the angle subtended at the center is twice the angle at the circumference. These are opposite angles of a cyclic quadrilateral. You've got a pair.
I see. Yes, I see what you're saying. Yeah.
You've got pairs of congruent triangles. There's a lot of things that your class can discover there, and it's a very nice investigation. And because there are probably 8 or 10 things that can be noticed about that, there's lots to talk about. Right. Now, we did this one. We showed this earlier. Caroline showed us by moving the point P around. And you can see it in the diagram, which I've drawn really large and clear there, that whenever you put the point at the top, at the angle here, you can see APB is half AOB. And I've called it, we showed this by moving P around, but now we can see that AQB is the same. It's half of AOB. So those APB and AQB are equal angles. But I've just told you that. I wouldn't, if I was a teacher, tell the class. I would ask them, what do you notice about? What can you tell me about? And see if they would answer those questions. So on the right there, you see
I've got to absorb what you're saying though here. Angles at the circumference subtended on the same arc. So sitting on the same arc. Angles at the circumference. So APB is equal to AQB. It's the same, but that's what we saw before. No matter where we put it, it was always half of AOB.
That's right. That's right. So if they're of the same side sitting on that arc, then they'll be equal angles because they're half the angle at the center.
All right.
Now then, what about this demonstration? Again, you can do it with the cardboard, but let's just look at what you can do with paper. Caroline's just showed you it with paper, but let's just look at the slide now and see what that is showing you. What we have discovered by measuring, and we've talked about it, is that the angle BAD, the bad angle, is equal to the angle BOD.
It's not bad, Toni.
It's half. I mean, it's not equal. It's half.
It's a good angle. No, but you said it's a bad angle.
Well, it just spells bad, doesn't it? The angle BAD is half BOD.
Hold your horses. BAD is half BOD. Yes, we saw that before. Yes. Yeah.
And what about, but that is angle Y that we're talking about.
Yeah.
Mm-hmm. But what about angle X?
Angle X. Now, angle X is, hold on. Angle X is twice angle BCD.
Okay. What can you tell me about X and Y?
X and Y, well, they total 360 degrees.
So BAD and BCD are half
BAD
of X
and
and half of
BCD.
Y.
So they're 180. So BAD plus BCD equal 180 degrees.
Hmm.
Okay, so
And
the opposite in a, what did you call it? A quadrilateral that's within a circle?
a cyclic quadrilateral.
Cyclic quadrilateral. Now, is that true for CBA and CDA as well? Or is it like the kite, where
Yes,
the
yes, because they're opposite. We could show that equally well.
so between them, well, if that's 108, that together make 180, and those together make 180, then the total internal angles of the quadrilateral are 360.
They all, but yes, but that's true for every single quadrilateral.
Yes, I know, but
in the
if
world,
you don't know,
whatever shape it is.
Yes, but if you don't know that, you can surmise that from doing this.
Yeah, but I think people will have learnt that before they come to do the circle theorem.
Yeah.
Yeah.
I think it's nice.
I think it's pretty. So let's move on. Now here we're going to be thinking about tangents. So Caroline has cut out about 2/3, I mean, partway around the circle, but not all the way around the circle, and left some of the paper there.
Hold on 1 second. Doobie-doo. Okay, right, we're ready.
So Caroline has made what you can see on my slide, and that is she has done this all by folding. Once she's cut out the circle, she's done it all by folding. She's folded along TO. Taking T
started off. That's how I started off, folding along the. So I've got literally an A4 sheet of paper folded in half along the length. Yeah.
And then she's opened it out, and she has found that point at the center of the circle. As you showed, we did by making another diameter. So you see that the center is where the two diameters intersect each other. And then she has joined T, she's drawn the tangents, TA and TB.
Yeah, and I chose those. T wasn't a specific place. I just chose two. I chose T, and then I drew tangents from T, so that to be sure that they were correct.
Yes, and she's just judged it by eye and made them just touch. The line TA just touches the circle. It's a tangent. It doesn't cut the circle. It just touches it.
Yeah.
And similarly, TB just touches the circle. And then you drew the dotted lines to join the point O to the point A, so OA and OB.
I've got my kite again.
You have. You've got the symmetry again, haven't you?
I do. So that means that plus that AOB plus ATB, those angles will be 180.
Well, I think that's a big assumption, Caroline, because those points aren't on A, O, B, and T aren't on a circle.
Ah, okay. So it's because they're in a circle, there's special things happen when you're looking at shapes within a circle.
But you're right, in fact. But you need to approach that. You are right, but you need to approach that a bit more slowly. Okay.
Okay.
So
I was just leaping to a conclusion there. I wasn't.
Yes.
Yeah.
Now I want you to investigate the two lines OA and TA and that angle.
Well, that's 90 degrees because
are you
it's
sure?
a tangent. Well, yeah, because it's a
Well,
tangent.
you can make sure it is by folding along AT.
Oh, folding along AT.
Folding along the tangent.
If I fold along the tangent,
and then fold along the radius OA.
This isn't going to be terribly, terribly precise. Now I've folded along the radius OA.
Now, Caroline knew that OA and TA are at right angles, right? But maybe you could demonstrate that again, Caroline. That they
I'm just going to check using the corner of my piece of paper.
Yes.
Well, I said the only reason I knew it was a right angle really is because I do remember when you're taught to draw the tangent of a circle, it is perpendicular to the radius.
But you
at
see,
that point.
but Caroline, what we want to do is to discover that, not to be told it.
Right, exactly.
So what we will, when we draw TA so that it just touches the tangent TA, so it just touches the circle, and then draw the radius, what we will notice is that that's a right angle, and we can check it.
So how else do we check it? Because I used my bit of paper. What else were you going to suggest?
Well, you can measure it with a protractor as well.
I got one of them.
Of course, this doesn't prove it could be 89 degrees, and you wouldn't be able to tell the difference.
Yes, that's true.
That's not a protractor, Caroline. That's a set square.
So it is. I got a protractor too. Oh dear. Adult brain. There we go. Protractor. And we've got, you can see that. So we got on there, and it is indeed 89 degrees. They're supposed to be 90.
Well, the thing about this is that these little discoveries are not telling you precisely what these measurements are, but they're suggesting, and then you've got a good reason to make a conjecture. So we're very keen on conjectures. That's just a fancy name for a guess, and then you have to try and prove it.
Right.
So what we've established by doing some paper folding and measuring, and everybody in the class measure, and some people will find that angle that Caroline found to be 89. Some people will find it to be 92. Some people will find it to be less than. Some people will find it to be slightly greater than. Some people will find it to be equal to 90. But across the class, there should be a consensus.
And it's just because, it's because it's what's the word? It's because they're errors. I mean, when we're drawing them, they're errors. But I've just worked out that AOB plus ATB is definitely 180, because that's 90 degrees and that's 90 degrees, because they are the tangents to the same circle that had the other properties for. So because that plus that's 180, then that plus that's 180.
Exactly. So in fact, TAOB is another cyclic quadrilateral, but there isn't a circle drawn there.
No, but
you could draw
it's
one.
The tangents.
Yes. Well, we've discovered.
Oh yeah, we could. So this would be a circle.
You could draw it.
There is a
do that now, but your class could do that, and they might.
And it's easy enough, because it's just half that. Am I correct? It's got to be. Is it?
Yes.
Is that going to be the diameter there?
Yes.
That will be the diameter. You just find the center and draw the circle.
Yes, you can do that. Well, we
Just the
won't
halfway
stop to
point.
do it
Okay.
now.
No,
but
no, that's fine. But it's beautiful, Toni. I think that's a nice little extra thing to do, is to actually
yeah.
draw that circle.
So if you're sort of clear about the questions you ask, then you'll get the children suggesting that those two angles are the angle OAT is 90 and the angle OBT is 90.
Yeah.
But the point is, introduce this before anybody tells them it is a fact. Let them discover it for themselves.
Yeah. It's fantastic. Fantastic.
So these are the instructions. You fold to make OT a line of symmetry. You draw tangents. This is what we've already said, so we're not going to do it again. We're going to draw the tangent TA on the folded diagram. So OA and TA are perpendicular. And then we can do it that way around. And then this is a little bit different to what Caroline did. And then we can prick through the paper to mark B, and we'll notice that OA and OB are equal. We can ask about that. And we can ask, what do you notice about triangles OAT and OBT? And we can ask, what does this tell you about TA and TB? And what it tells you is what Caroline said earlier, that TA and TB are tangents, and they are the same length. So the tangents from outside a circle from an external point, that's a point outside the circle, are equal in length. So that's another nice little experiment. Okay. Now here's something that is a little bit more difficult. So Caroline, did you prepare this one?
I did. I just did as much as you had on there, and then I thought, well, you'll give me instructions from there.
Okay, so here what we want to see is Caroline has drawn. I think if you make that turn it round so it's tilted so that it looks like the diagram on the screen. Okay. And now you've got the horizontal line is the line TA.
I'm going to make it a little bit darker. The horizontal line is the line TA. Okay. Oh, there it is. Yeah, I didn't put the letters in. A, T. I'm not sure where T goes, but that's TA.
T can be anywhere, really.
Anywhere, right. Well, it is anywhere. It's just wherever. Okay.
So that's a tangent. That's a tangent.
That's the tangent.
Okay. And now you've got, I think you've got them drawn faintly. You've got the center marked, haven't you, Caroline?
Yeah, I do. The origin,
so can you draw TO, which is the radius? Sorry, not TO.
AO. Dotted or solid?
Dotted, I think, is better. AO.
Okay.
And OB.
OB, which is another radius. Now, where's OB? I've got OB. Is that random? Well, how is OB?
B can be anywhere.
Okay.
B can be anywhere on the circle. Okay.
Okay. Right.
And now draw the chord AB.
That's B. Let me write letter B in there.
With
AB.
Not a dotted line. This one.
Solid.
Hmm.
There you go.
Now, we have just been talking about the angle between the chord and the tangent.
Yeah.
We've been talking about the angle between the radius and the tangent.
Okay, that one's 90 degrees. I'm not sure about the angle between the chord and the tangent.
Well, call it X. It can be. We don't want to know what it is, and we don't really need
to know. So this
just call it X.
Is X. This is 90 degrees. So X plus whatever that is, and that's an isosceles triangle because that's the radius and that's the radius. What else?
Well, the two angles at A, you've marked 90 degrees, and the other two angles have to be 90.
They add up
So
to
the one
90.
that you haven't marked has got to be 90 minus x.
Okay, 90 minus x. Right, so now we have only one unknown.
Right, now can you see another angle that's not equal to angle OAB?
OAB, yes. OAB, yes, it's OBA, because
Well,
that's
and
an
that also
isosceles
must
triangle.
be 90. That also
Yeah.
must be 90 minus x.
And that's, we don't know what that is. We know that that is twice, what's the letter there? P.
No, Caroline, look at it. No, don't go to
I'm
P
not doing
yet.
anything. No, I'm not doing anything. I'm
No,
just
no,
marking it
no,
because I hadn't
no.
marked it.
No, that's fine. But look at it. We're still looking at triangle OAB.
Yep, OAB, yes.
So what do you know about the angles of a triangle?
They add up to 180 degrees.
So we've got two of the angles. So can you tell me what the third angle is in this diagram?
180 minus, well, okay, so it's going to be 180, blah, 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 blah. It's going to be, I'm going to write it down here. It's going to be 180 minus 2 times 90 minus x. But that looks like I'm going to have 180, which doesn't make sense. So yeah, it's 180 minus 180 plus x. So that angle there
Plus
is
x, Caroline.
That angle there is x.
Look at it again. Look at your little bit
Yeah,
of
it's
calculation.
X. Yeah, it's x.
Well, Caroline, I think you better
It just
try doing
leaves
that.
x.
No, what about the
2x? 2x. Sorry. I've got to spot the mistake on my classroom whiteboard. You know that, right? And they've got to spot the mistake.
Because
the mistakes happen
now, Caroline,
a lot.
what about AOB and APB?
AOB and APB. Well, we know that's what I was saying. Yeah, I was leaping ahead. That's what I was doing. So we've already we know that APB is half of AOB. Therefore, APB is x. Have I got?
Yes. Yeah. So look at what's written on my slide. The angle between a tangent and a chord drawn to the point of contact is equal to the angle at P, actually, that chord subtends in the alternate segment of the circle.
Sorry. Oh yeah, I've got to sit down and think about that. I've really got to sit down and think about that. Hold on.
Just stop playing with your picture and have a look at the words. Look at the words.
Right, hold on. Let me read it, Tony. Let me read it. The angle between a tangent, so this is the tangent, and a chord. So it's angle x. We're looking for the angle x here. So the angle between the tangent and the chord, which is that angle x, drawn to the point of contact, which is a chord joining, which is point A, yeah, is equal to the angle that the chord subtends on the alternate segment of the circle. So, and that's out there. That's anywhere out there.
Yes, it's not the segment that's down at the bottom below AB. It's the one above AB. That's the alternate one. It's the one that
it's the first one that we were looking at, the first elastic band that kept flying off.
So now
that angle there is equal to that angle there.
Exactly.
Oh my goodness. So the angle, let me just redo that in my head. The angle, so we've got the chord. We draw a tangent at the chord. The angle between the chord and the tangent is the same as the angle if we take any point in the, what did you call it?
Alternate
in the
segment.
Alternate segment. up there, it's the same angle. Ha! Ha!
So, okay, let's move on. So I want to show you this street because it is in a place called Massapumalele. And for nearly 20 years, I've had a flat very close to that, a flat. But it's not in a shack like that. It's actually rather a nice flat by the beach. But very close to where I live, people live in those conditions. And that isn't a long time ago. It's absolutely what it's like now.
Today.
It's a swampy area where these houses are built. And when there's any rain, it floods like that. And you see, they don't have running water in the houses. People have to go, as you see that lady is, with some sort of container to fetch water to bring
they
it
have
home.
standpipes, but they also don't have toilets. They have shared portaloos, and to do their cooking and their washing up. It's like camping. It's the same arrangement.
Well, it's their life, and you see above there the lines there. They are taking electricity to each shack, each house. Okay, and the people who live there, a lot of those people, the ones who are lucky, the lucky ones, have jobs in Fishhook because there's shops in Fishhook and restaurants, and they maybe work as a gardener or cleaner or some other job in Fishhook. But these lesson resources that we publish, and there are hundreds of them, and we publish a new one every day on the AIMSEC Facebook page, and we talk about them on Happy Maths Hour. They're freely available to everyone. And AIMSEC supports and empowers teachers in the most seriously deprived communities in Africa. And that is just down the road from where I live, but just down the road from every area where there's some comfortable housing and shops and people are living in comfortable conditions. There are other people living in townships, not all as bad as Massapumalele like that. And Massapumalele isn't all like that, but it is a poor community, and many of the people don't have jobs.
And so the teachers that we work with AIMSEC, they want their children to have a better future, the children that they teach to have a better future.
But the schools are not, they've got big classes and not many resources. But we try and help the teachers by giving them free resources and lots of ideas so that they can make their lessons so good that the children will have a better education and they'll get good results at school. And that's the whole aim. And then the children might escape the life of poverty by getting a job if they got a good maths matric result, and especially if they can go on to some further training or to higher education. The idea is that we're empowering the teachers to give a better education so the children have a chance of escaping poverty. Now, we're asking you to make a donation to support the work of AIMSEC, whatever you can afford. There is the link to that to make a donation. So if you use our resources, and if you like our Facebook page, the AIMSEC Facebook page, where you might be watching this Happy Maths Hour, or the YouTube, or you use the Aiming High resources, and you just give us the price of a cup of coffee or less, and you don't have to do it every time you use the resources, just now and again. That will make a huge difference because it enables us, as Caroline and I and many others are working as unpaid volunteers, it will enable us to give the teachers bursaries so they can do our courses and get the benefit.
Now on that link that's also in the description, by the way, you can make a monthly donation as well. You can set it up so you can make a monthly donation.
And here are the links to a good description of investigating circle theorems with lots of detail, and that your children, a worksheet that you can give to children to work through. And then there's a workshop guide. Run your own workshops on investigating circle theorems. Teachers might like to look at that and share that workshop with other teachers. And then there's a movie about paperclip compasses there, and there's the link to it. And then there's the link for making a donation again. So our hour is up, and so I think it's time to say goodbye.
Thank you for joining us, and we'll see you next time.
Goodbye then. Thank you for joining us.